Welcome to The Explainer. So today, we're going to tackle a classic chemistry puzzle, one that kind of seems to defy logic. How is it possible for two totally different acids to give you the exact same level of acidity? We're going to solve that mystery, and along the way, we'll figure out how to use their unique personalities to create some really cool chemical systems with pinpoint control.
All right, so here's the challenge, right at the center of it all. Imagine you've got two different acid solutions. You stick a pH meter in both and boom, they read the exact same thing, a pH of 1.0. Now here's the twist. One of these acids is notoriously strong, and the other one, well, it's weak. So how on earth is that possible?
Okay, let's meet our two contenders. In one corner, we have hydroiodic acid, or HI. This stuff is a textbook strong acid. In the other corner, we've got iodic acid, HiO3, a known weak acid. Now we know the strong acid's concentration. It's 0.1 molar. But the weak acid's concentration? Well, that's a big question mark. And that's the first piece of this puzzle we need to solve.
So, to really crack this thing open, we first have to get behind what makes an acid tick. We gotta understand its secret identity. What do strong and weak really mean in chemistry? You know, it all boils down to one simple thing. How willing is an acid to give up its protons?
Think of a strong acid like HI as an all-or-nothing kind of player. The second it hits the water, every single molecule just completely falls apart. It dissociates, breaks up, and throws its proton out there. It holds absolutely nothing back. It's a one-and-done deal.
And you'll notice that arrow there is pointing just one way, to the right. And that's super important. It means this is a one-way trip. Once those HI molecules break apart, there's no going back. They don't just magically get back together. And you know what? This complete irreversible split is exactly why calculating the pH of a strong acid is usually so straightforward.
Okay, but then you have a weak acid, like our HiO3. It's a lot more cautious. It doesn't just give away all its protons like that. Instead, it sets up this really delicate balance, an equilibrium, where only a tiny fraction of its molecules are actually broken apart at any one time.
And this really shows the difference perfectly. See that double-headed arrow? That's the whole story right there. It means the reaction is totally reversible. So while some HiO3 molecules are busy donating protons, other ones are grabbing them back and reforming. It's this constant back and forth, a non-stop chemical dance.
Okay, so let's think about that. We have this equilibrium, this chemical dance. If the weak acid is so stingy with its protons, what does that mean for its concentration? I mean, to get the same pH, which means the same number of free-floating protons as the strong acid, you'd have to start with a whole lot more of the weak acid to begin with, right?
And yep, the math totally backs us up. Big time. To get that target pH of 1.0, you need a solution of iodic acid that's around 1.8 molar. Think about that. Because only a tiny fraction of those molecules are actually giving up a proton, you need a whopping 18 times more of the weak acid just to match what the strong acid does without even trying.
All right, so puzzle number one is solved. But now, let's take that idea and build on it. Turns out, we can actually harness that special equilibrium property, the whole chemical dance thing, of our weak acid to create something incredibly useful, not just in the lab, but in our own bodies. We're going to make a buffer solution.
So what is a buffer? Well, think of it like a chemical shock absorber. It can soak up extra acids or bases that you add, and it keeps the pH of the solution incredibly stable. The secret sauce here is what we call a dynamic duo, a weak acid and its partner, the conjugate base. And the conjugate base is really just what's left of the acid after it's donated its proton.
Okay, so let's say our goal is to make a buffer that sits right at that same pH of 1.0. If you look at the chemicals we have on the shelf, which pair do you think is the right one for the job?
Well, the choice is actually pretty straightforward. You just can't make a buffer with a strong acid. It's impossible. Remember how it's a one-way street? It dumps all its protons at once, so there's no equilibrium, no back and forth to absorb any changes. It's only the weak acid, our HiO3, paired up with its conjugate base that can create that stable, pH-resisting system we're looking for.
So, to get the recipe for our buffer just right, we need to pull out a special tool. It's called the Henderson-Hasselbalch equation. Now, I know it sounds a little fancy, but this formula is basically the key. It perfectly connects the pH we're aiming for, the acid's unique personality, its pKa, and the ratio of the base and acid parts we need to mix together.
And it's really just a matter of plugging in the numbers we already have. We know our target pH is 1.0. We know the pKa of our iodic acid is 0.77. So the only thing left to solve for is that magic ratio of base to acid that's going to make it all work. So we run the numbers through the equation and out pops our answer. We need to add exactly 8.8 milliliters of our conjugate base solution to our original 25 milliliters of iodic acid. And that very precise recipe, that's what gives us our perfect buffer locked in right at a pH of 1.0.
But wait a minute. What if you look on your shelf and you don't have that conjugate base salt just lying around? No problem at all. Chemistry has another, kind of more clever way to do this. You can actually make the base you need right there in the beaker.
This method is called titration, and here's how it works. You start with just your weak acid. Then you very carefully start adding a strong base, drop by drop. This strong base reacts with some of the weak acid, it neutralizes it, and in the process it converts that acid into the conjugate base you need for your buffer. You are literally making one of the key ingredients from the other. It's pretty cool.
Now, of course, just adding one little drop of base isn't going to cut it. To be really effective, to have some real muscle, a buffer needs a good amount of both the acid and the base parts. That way, it can fight off threats from either direction. So the question is, how much of that strong base do we need to add to get our buffer into its active zone?
And this right here is the key. A buffer is at its absolute best, its most powerful, when the solution's pH is super close to the weak acid's pKa. Why? Well, because that's the sweet spot where you have hefty amounts of both the acid and its conjugate base just ready and waiting to neutralize anything you throw in there. The rule of thumb is that this active range is the pKa plus or minus 1 pH unit. So for our acid, that's a pH range from about -0.2 all the way up to 1.8.
So, to create just enough of that conjugate base to get our foot in the door to officially enter this active buffer zone, the calculation shows we need to add a minimum of 1.14 milliliters of that strong base to our iodic acid solution.
Okay, so let's take a step back. We started with what seemed like a simple question about pH, right? And we ended up building this really cool, stable chemical system using two completely different methods. But what's the big picture here? Why does any of this stuff actually matter outside of a chem lab?
So let's do a quick recap of what we've figured out. We've seen that the huge difference between strong and weak acids all comes down to that reversible equilibrium, that chemical dance. We learned that this equilibrium is the secret ingredient for making buffers, which are absolutely essential for keeping pH stable. And we've now got two different ways to make those buffers in our chemistry toolkit.
And listen, this isn't just some theoretical exercise for a test. The single most important buffer you will ever encounter is working inside your body right now. Your blood is a finely tuned buffer system that maintains a super precise pH of about 7.4. Just think about that for a second. What would happen if it wasn't a buffer? Even the tiniest shift in that pH would be, well, catastrophic. This is, quite literally, the chemistry that keeps every single one of us alive. Thanks for watching The Explainer.